Hi everybody. Today's our topic is LTE Coverage Optimization. It is a very important aspect in an LTE network if you consider it from the initial phase, from the deployment phase, and from the ongoing optimization phase. We will be covering a number of topics within LTE Coverage Optimization, and those are: number one is how to detect downlink and uplink coverage problems, from which KPIs, from which network information we can detect that. And secondly, we will have a look at the imbalances between downlink and uplink, and the imbalances that can occur between the transmission elements from the E node B. Thirdly, we will discuss overshooting and overlapping problems, and then we will have a look at extended coverage, and then we can look at cell border adjustment, and finally in the end we will look at the parameters that we can use to optimize LTE. So let's begin the video, and by the end of this video you will have the grasp to optimize LTE coverage and work on LTE coverage wherever you are working. So let's get to our first topic. So the question is how we detect that we have a coverage problem. So before detecting a coverage problem, we need to know in terms of RSRP that what actually is a coverage problem. So in terms of coverage whole, the RSRP, if it is less than 120 dBm, then we consider it as a coverage whole. And in terms of weak coverage, RSRP is less than -105 dBm. So this is regarding the downlink. So this is your coverage whole, and this is, so you have a weak coverage problem. So when optimizing coverage, you have to have a balance between the coverage and the interference, because if you are increasing transmission power, you're also increasing interference. So we go back to our question that how we detect coverage problems. In the downlink, if you're considering this is your base station and this is your UV. So how we detect it, that we have an LTE coverage hole? One of the best ways is basically your drive testing. If you're having a drive testing done for a cluster or for a number of sites, you will get that information where you have handover failures, where you can see in the drive test that you go into no coverage areas. But you can also see it through the KPIs. So for example, for a number of neighboring sites, there is one specific point at inter-site distance where you're having a lot of IRAT handovers. So in that situation, that shows you that you most probably have a LTE coverage hole. So that would also point out sometimes in terms of weak coverage, you will have handovers towards the other LTE sites, and you will have low throughput, and you have RSRQ issues. So this is how you go through towards downlink. What about uplink? So in LTE we have a factor called power headroom, and power headroom report is sent by the UE towards the E node B. And in that power headroom report, the UE reports that how much room it has from its maximum transmission power. So basically the E node B knows that is the UE transmitting on maximum power or something below that. So basically power headroom has a range from -23 to +40 dB, and if you normalize it, it goes to -5 to 20 dB. So your E node B would know from that power headroom that if your UE is already transmitting on maximum power, then yes, it is in a part where there is a weak coverage. Secondly, we have SINR thresholds for your physical uplink shared channel, and we have RSSI thresholds for your uplink shared channel as well. So for the E node, we can move from those thresholds as well, that the UE might be facing an uplink coverage problem. So these are the ways how you detect downlink and uplink coverage issues in LTE. So let's move towards the next topic, that is overshooting and overlapping. So let's discuss overlapping and overshooting. First, we'll discuss overlapping. Overlapping basically means in LTE that you have at one coverage area more than there's no dominant server. So there's a lot of you can say pilot pollution, and the reference signals from different cells are within a certain range. So there's no dominant server, and you can have strong signals from a number of E node Bs, and this will result in downlink interference, and in the end basically will result in low throughput, and sometimes it can result in even in real link failure as well. So what are the criteria that basically we use to decide that we have an overlapping issues? So a general rule of thumb is that if in an area, for example, this is a coverage area, and we have in this coverage area more than 3 RS, which are basically greater than -0.05 dBm, and the strongest reference signal is not more than, it's less than 6 dB from the rest of the two. So within a range of 6 dB, for example, if we have the strongest signal at -81, so from -81 to -87, we have 3 reference signals. So this will result in pilot pollution and will in the end result in downlink interference. So how to control these factors? Basically, you can use azimuth tilting, you can use e-tilting, you can use height reduction, and basically sometimes you can reduce the power of reference signal as well, or you can adjust boosting or deboosting or reducing the power of the reference signal or the common channels, or even the power ratio between the downlink shared channel and the PDCCH. So this is one issue, which is basically your overlapping issue. Overshooting issue basically is when your the signals from your base station are reaching places they are not supposed to. So basically you have the case of more coverage than you have predicted or than you have expected. So this can be caused by, first of all, maybe bad modeling, secondly because of wrong parameter settings in terms of e-tilting, in terms of height, in terms of some other power parameters. We need to see that how basically we go and optimize that. But if I have to detect overshooting, we can detect it via your dry testing. We can detect it via your propagation delay matrices. So you get these propagation delay matrices in your OSS KPIs, and from this you can actually get the information that from how far the cell is getting this traffic. And overshooting cells basically cause a lot of problems in terms of handovers, because handover relationship is defined in terms of normal coverage relationships, how you have modeled it, how you expect it, and if a site is providing signals where it is not supposed to, then the neighboring sites will not be added in its neighbors, and you might have a handover failure. The third part is your timing advance. You can get this information from your timing advance as well, and that is included first of all in your random access message and in your connection acceptance message as well. So you can get that information, and you can also check that you have an overshooting set. And DT is the most common, but you can use these two as well for your overshooting issues. And again, you can use tilting, you can use parameter optimization to reduce your coverage and improve your network performance. So now let's move to imbalance in downlink and uplink, and then we'll see the TRX imbalance as well. So let's discuss downlink and uplink imbalance. So if you have a uplink imbalance, that means that, and that is usually the case, that you have an uplink limited network, or you have an uplink limited coverage, and that means that your RSRP from downlink is greater than -105. Your power headroom, which we discussed earlier, which your E node B sends to your, which your UE sends to your E node B in terms of your how much power it is left for the UE transmission power. Your power headroom is less than -3 dB. Your received interference power is less than -105, and your uplink SANR is less than 90. So this shows that you have a good downlink. You have low interference, but you have poor uplink, poor up. So this is uplink imbalance, and usually it is the case that we have better downlink coverage because E node B is transmitting at a much higher power, and we have this problem usually at the cell edge. And if we have this problem, then we need to either limit the coverage, or we need to have a drive test and see from where we're having this imbalance of issues. And these imbalance issues can also come because of hardware issues. For example, your diversity issues in your E node B, or your combiner, or your other losses in the uplink direction in your hardware. So you also need to check that as well. Second is your downlink imbalance. Your downlink imbalance comes where your power headroom is greater than, for example, it can be greater than 0, or it can be greater than 3 dBs. Your received interference is still okayish. Your uplink SANR is greater than 3 dBs, but your downlink RSRP is less than -110. So this is the case where your downlink has the issue, and your network is downlink limited. And for this case, we need to see either your cell is transmitting the maximum EIRP it can transmit, or is there some issue with the hardware, or is there some issue with the modeling, because there can be some issues with the modeling as well, or there is some coverage enhancement required, or there is some blocking, some building, some penetration loss, anything that can cause this. But this is how you basically detect having an imbalance between downlink and uplink. Then we have another issue called TX imbalance. Your TX imbalance basically causes problems when two transmission elements from the same antenna system have different performance. This can be because of a connector loss, because of some feeder loss, or anything, but one antenna element will be providing you better coverage, and the other antenna element may not be providing you any coverage or lower coverage. And if you have seen optimization tools, if the optimization tools which can detect element messages, you can have coverage from TX1, you can have coverage from TX2, like this. And if you see the coverage of TX1, it might be better than TX2, and that is basically your TX1 and TX imbalance. And in that case, it basically directly means that you have a hardware issue, and you need to check that. So this was our imbalance issues. And now let's go to extended cell coverage and how we do the cell border adjustment, and then we will see the parameters. So let's discuss extended cell range, and then we will see how we adjust cell borders as well. So in LTE, the maximum cell radius can be 100 kilometers, and that is as per your 3GPP standards. But the interesting thing is that PRACH, the physical random access channel, has different formats in LTE, and if you want to optimize your cell extension, so you have limited number of PRACH formats that you can use to basically have an extended cell coverage of different radius. So it is a combination between PRACH format and your special subframe format. So these two, when you are basically designing your network, you will choose a format for you in combination with PRACH and your special subframe format to provide a particular radius. And for PRACH format, you have 0, 1, 2, and 3, which have adjustable cell radius. So this is how you configure it. And what are the problems if you extend cell coverage then we can face? Number one is basically your delay. So if your PRACH is being sent from, for example, a distance of 30 or 40 kilometers, so it can happen is that the E node B does not get that PRACH in the required single duration, and therefore it will be discarded. So we need to plan the network, and we need to plan the PRACH in special subframe structure according to that. And second problem is basically your orthogonality. PRACH uses a sequence called ZQ, and this is an orthogonal sequence from the PRACH preamble being used by some other users in other cells as well. But if your delay is too long, then basically your cycle prefix, which is basically used to counter these delays, this cycle prefix may outlast the delay. Basically your delay may outlast the cyclic prefix, and therefore you will lose orthogonality, and therefore there will be issues in your preamble decoding. And the third issue is your SINR for your RACH and other channels, because the distance is large, and therefore you will be doing an uplink limited system where your SINR is low, and therefore you would need to basically allocate more uplink resources to counter that delay, to counter that SINR problems. So that is regarding cell extension. And regarding adjustable borders, basically what we do is we have two parameters. We will discuss this parameter when we go into the parameter section, but that is QRXLev min, and then we have A2 threshold. So QRXLev min is basically your minimum RSRP level required to access an LTE cell, and A2 threshold is basically the threshold where your LTE cell will basically go towards your other RAT. So basically this is two coverage areas, and using your cell border adjustment is like this, that you keep either of these two same, and then you can reduce or increase these parameters to adjust your cell border if you're having an issue. For example, if you have an uplink limited system and you are having issues with radio link failures and other stuff, you reduce the cell size. Or you can increase your cell size if your cell has satisfactory performance plus a hysteresis from the performance KPIs. Then you can also increase the cell radius as well using these two parameters. So now let's go to the parameters and see what parameters we can use for our basic LTE optimization. So we are at the last part, and that is the parameters. So we'll discuss first the downlink parameters. So here are the downlink. So the first parameter is a very basic parameter, and that is your QRX length. QRX length is basically your minimum threshold required basically to access the LTE cell in an idle mode. And an interesting part is, if you see in the drive testing, you have to multiply that with 2 to get your actual threshold. So if you see it in the drive testing element, i.e. as neg 65, you divide over 2, and that is your actual threshold. Then you have your reference signal power, and with reference signal power you also have some parameters called P alpha and then P beta. Now these have some relationship in terms of how you allocate reference signal power in your OFDM symbol, because the symbol power needs to remain, the whole power needs to be the same, but in some symbols you have your reference signal and in some you don't have. So these are the ratios basically which define how higher the power of reference signal will be and how you will basically compensate for lower power in some of the other symbols. We will definitely discuss it in our LTE optimization course that will be uploaded most probably in the second week of March, where we discuss LTE optimization in a whole, in terms of coverage, capacity, interference, latency, mobility, and do look out for that. Then we have our offsets, and these offsets usually are not set primarily directly through parameters. Some of them for SCH, then for VCH, then we have PB offsets for the downlink shared channel, and all of them are related to your power control as well. Then you have your uplink parameters, and in uplink you have your alpha. This is your fractional power control parameter. So if your alpha is set to 1, your power control only focuses on path loss. It does not focus on your interference or throughput, and the value can be from 0 to 1. So your power control can be directly skewed towards your path loss, or it can be directly skewed towards your interference. Then you have your parameter that is called P0 nominal, PUSCH, and PUCCH. So these are basically the parameters which control your power control algorithm for uplink. So your E node B will try to keep your you can say receive signal power to this level had during your power control. Usually for common control channels it's neg 117, and for your shared channel it is neg 103. I remember this from my Ericsson days. So these are the nominal parameters for your uplink power control. Then basically if you go into a bit of detail, then you have your initial SINR target for your physical uplink shared channel. Then you have your max SINR target for physical shared uplink channel, and your minimum SINR target for your physical uplink shared channel. So these are some of the parameters which cover your coverage, and you can use them for optimizing your coverage, and also they play a part in your power control as well. And we will of course definitely discuss power control in much more detail in one of our optimization program. One thing which I also wanted to mention was PDCCH boost, where we basically aggregate different CCEs to provide a boost to PDCCH coverage, because usually Your PDCCH does not use any beamforming. Your majority of your beamforming and your coverage enhancements are used for your downlink shared channel. So sometimes there is a coverage gap between your your shared channel, downlink shared channel, and your PDCCH, and therefore we use a PDCCH boost. I will do a separate blog on that because that's a very interesting topic. So that's it for our LTE coverage optimization. I hope you have liked our tutorial. Do subscribe to our channel and also have a look at our website for our upcoming trainings on LTE, 5G and other things. Thank you so much, and let's meet another day for another lecture.